And hi, everyone at home. Hi, everyone in the room. So if you happen to stumble in here unawares and are thinking, where are we? What are we doing? We just kind of started a lecture series for no reason other than, let's try it. And it ended up being popular far more than we thought. And then so in the spring we did it again, and then in the summer we did it again. And then they've mostly been wildlife based. But I teach a lot of classes and, I love teaching stuff. And so I thought let's see if anyone has any interest in this, not only because, I mean, the human body is just amazing. All right. Also, it just helps to understand how we work. But also, I'm sure, no need to go into personal stories, but I'm sure all of us, or many of us, have all of a sudden, unexpectedly, been in a doctor's office or a hospital room for ourselves or a loved one, and all of a sudden, there's these tests being thrown around, and all of a sudden, like understanding what's going on to help make the best decision. This was something maybe you weren't prepared for, so it just kind of the thought that let's just talk about different parts of the human body, and just kind of. I remember I read a book once. It was on a part of the anatomy, but it said like a user's manual, and it just hit me as funny as there's user's manual for everything. Like why not one for the human body? We're doing a little series. So we talked about the biology of gender. We talked about the blood and blood tests. Tonight, we're going to talk about the heart, the ECG, and that's probably all we have time for. But if we wanted to throw in a little about blood vessels, if time permitted, that'd be fine. Next week, we'd like to talk about the most complex structure in the known universe, the human brain, right? So how that works, so that's near and dear to my I was going to say heart, but mixing up my topics. And then 2 weeks from now will be the last one in the anatomy series before we kick off a wildlife series in the fall. Once again, very similar, close to the same as what we did last fall. And that will just be, we'll start looking at other systems, respiratory system, digestive, urinary, and just see how much we have time for. Just hit some of the major concepts. Any thoughts or questions before we begin? Okay, so let's just say I start talking, or and you have a reaction, maybe because of this, maybe because of the music that you just listened to, and you're thinking, I hate this. Like this is horrible. I'm in the wrong place, and you just want to walk out of here. All right, now just on the way here, I'm sure this applies to a lot of you. You just got new shoes. All right, and you didn't buy socks. But anyway, so you got these new shoes and no socks, and you just start walking, and your feet just start rubbing and rubbing and rubbing as you walk away from here as fast as you can. What happens to your feet before too long? Blisters. All right. Now here's a question. When does your heart stop rubbing against your lungs? There's two answers to that question. When does it stop rubbing against your lungs? We're not using that one. Never is the answer we're going for. Never. So here you are. So how can just after a half a mile you got a blister on your foot because the rubbing is annoying, but your heart is moving all the time, your lungs are moving all the time, your intestines, your stomach. Well, it turns out your organ systems in this body cavity, they're wrapped in bags. Now today we're talking about the heart bag, which we call the pericardium, but the same would apply to these other organ systems, which we can mention later. So there is a bag around the heart. Actually, I just zip back and forth depending on what I feel most drawn to at the moment. So if you were to say, I want to see a heart, all right, and you look at, I think this is an opossum, you realize I can't see it because it's in a bag. All right, if you say, I want to see it in a cat, you don't really see the heart itself until you put a hole in the bag. So the heart comes in a bag, which we call the pericardium. And it has two layers which are very smooth and a space in between where there's a lubricating fluid. So you have two layers of the pericardium, a pericardial space and a lubricating pericardial fluid. And now as a result, you've just had this friction-free environment where the heart can just move and move and move without those blisters and adhesions we would worry about anywhere else. So this never goes awry unless you develop like a tear, and then you would lose some of that fluid, in which case that might be a problem. If you had an inflammation of the pericardium, now fluid might build up here and now have a little extra pressure. So that might be a problem. One friend once he had some tests done and they thought he was having a heart attack, and they kept him admitted like for a week because all his blood work was coming up funky, like he was having a heart attack, but his heart seemed fine. He had a tear in his pericardium and stuff was leaking out, and that was throwing off the test. So every now and then, there's a test, that comes back involving the pericardium. Okay, before I start, I'm sorry, I might make some of you angry or hurt your feelings. So I apologize. I have to say it. Nobody hearts you. Sorry, it just doesn't happen. All right, no one ever broke your heart. You don't wear your heart on your sleeve. It goes back a couple thousand years ago. All right, there was this debate. All right, there was like Hippocrates, father of medicine on one side, but then there was like Aristotle and all these people on the other side. And the question was, where do we think from? Where do we feel from? All right, Hippocrates says, I think it's the brain. All right, but he was in the minority. Almost everybody else, the Egyptians, you remember Osiris weighing the heart, in the afterlife to see if you've been a good person. Everyone else thought it was the heart. And Aristotle, even said, here's logical proof. If I look over there, all right, and I see someone I find attractive or something that frightens me, what happens? My heart starts beating faster. Logically, that heart is the seat of emotion. That makes perfect logical sense. It's wrong, right, but it makes perfect logical sense. So, that was way back then. If you think back to your last, Valentine's Day, we still do it. I heart you, or no, you don't. All right, it should say like I hypothalamus you, or he or she broke my septum pellucidum, but that's the brain, and we'll talk about that next time. So, they mixed it up 2,000 years ago. We should stop mixing it up. All right. So the heart is a pump. It is about the size of a closed fist, and it kind of looks like a triangle. So we use terms, that you may remember from geometry whenever you study triangles. We have a base and an apex. The base is up here, and what we'll call the second intercostal space. The fancy word for ribs is costa. The spaces between them is intercostal. All right, so where the space around the second ribs, that's where the base of the heart is, and the apex of the heart is around the fifth intercostal space. Now, the next thing I say usually makes me seem cool. I'm not quite sure it's going to work in this audience, but we'll try. The apex of the heart is not here on the midline. It scrunches over a couple of inches, about 5 inches to the left. All right.
What are we listening to?
Hi, I'm just going to mute you if you don't mind. There is a gene called Sonic Hedgehog, and you're asking, is there a gene named after a video character? Yes, there is, and it's a really important embryonic gene that determines how embryos develop, and it has a role in making the heart scooch over to the left. Every now and then, someone has a mutation in that, and their heart scooches over the other way, scares their doctors. But the apex of the heart scooches a little to the left. We have 4 chambers of the heart. 2, the atria, are small and up top near the base. The other 2 make up most of the heart, going down towards the apex. All right. There are grooves between them, and in those grooves we've got blood vessels. Now, these blood vessels are super important. Maybe we get them back to them later, but let me just kind of really quickly show you a picture and ask you a question here. So let's say that if this is the muscle of the heart that needs oxygen and sugar in order to contract and squeeze, and there is blood in the heart that has oxygen, where does this muscle that needs oxygen get its oxygen if it's holding blood that's full of oxygen? Does it get it from the blood in the chamber? No. This is going to the brain, the arm, the foot. That's not going to the heart. All right. So this muscle needs artery and veins, just like my brachial, just like my arm muscles have their own arteries and veins. My heart muscle has its own arteries and veins. So if we want to talk about heart disease at the end, happy to. That would involve plaques developing and narrowing these blood vessels here, because even though there's oxygenated blood in the heart, that's not what's supplying the heart muscle. They have to get it from arteries and veins, just like these blood vessels do. Okay. Right. So first thing we always have to do, all right, is I'm going to zip through this really fast. I'm going to talk about how blood goes through the heart. Now, if I go through it too quickly and you're saying, oh, like my students would say this, like if only he would go through that like 16 more times, you're in luck. So this is just, we have to do it once just to kind of set the stage, but this will come back, if you say that was so fascinating, but he went a little too fast. So let's just, paint the big picture first. Right now, you have red blood and purplish blood. All right, now in this animation, it's going to be exaggerated, but only a little. When oxygen binds to hemoglobin, it does become more of a scarlet. And when hemoglobin loses oxygen and carbon dioxide binds, it becomes a purplish blue, which we call cyanotic. Right, so someone's in shock, or when someone's taken the poison cyanide, they'll develop a purplish blue pallor. So when oxygen is bound to hemoglobin or not, it changes color. So the red and the purplish blue. Based a little exaggerated here, but it is based on. Right now, your brain, your hand, and your foot have blue blood. They don't want it. All right, it was like they took the oxygen out. All right, so they want to get rid of it. So they put it into veins, and the veins come back to the heart. There are 3 things that are coming into the heart bringing blood. All right, one is draining the top part of the body, called the superior vena cava. Now, everyone in here, if you want to follow along at home, you're welcome to. So if you've got a big blue thing coming in from the top, that's the superior vena cava. If you've got a big blue thing coming in from the bottom, that's the inferior vena cava. Feel free to pass your hearts around. And then there's a third thing that brings blue blood from the heart itself, called the coronary sinus. So there's blue blood here, there's blue blood there, there's blue blood here. So all the blue blood that nobody wants goes into one of the 4 chambers, but only one, called the right atrium. Right. So blue blood that nobody wants comes into here. Okay. The right atrium receives that and then sends it to the big chamber that's right under it, called the right ventricle. All right. Oh, and by the way, sorry, this is more funny if we dissect a cow's heart, but I have to warn my students all the time with this. Okay. So when we say like right or left, it's based on what the structure looks like. All right, it's not that it's on your right hand side, because I've seen students like, all right, so I'm dissecting this cow heart, so here's right, here's left. All right, well, if I'm a cow, it's like right hoof, left hoof, okay. Or maybe I'm like this, right. I mean, it's hilarious to watch, but that's not how you figure it out. All right, so we're going to talk about how you figure it out. There is a right atrium and a right ventricle. The right atrium sends the blue blood to the right ventricle. The right ventricle squeezes and this blue blood leaves. Does it go to the brain, the hand, the foot? No, they just got rid of it. They don't want blue blood. They want red blood. This is not red blood. How do we turn blue blood red? We can only send it one place, the lungs. So this is what's called the pulmonary trunk. All right, so coming out of the right ventricle, there was a pulmonary trunk that is going one place and one place, only the lungs.
Of this, this is the ibuprofen cream
For
generic.
Where did we go? There we go. So it sends it one place and one place only, the lungs. And there in the lungs, we have gas exchange that we can talk about in 2 weeks. And so oxygen from your inhaled air goes on hemoglobin. And now this blue blood now comes red. All right. So we had blue blood that we sent to the lungs. Red blood now comes back through pulmonary veins. So we have, I'm sorry, this is the bad one. Or like this doesn't fit. All right. So on the back of your heart, you should have these 4 little red tubes. These are pulmonary veins coming back from the lungs into the left atrium. The right atrium receives the blue blood. The left atrium is receiving the red blood. So all this blood's coming back to one chamber only. This red blood goes from the left atrium down to the left ventricle. Now we got the left ventricle full of the red blood that everybody wants. So the left ventricle squeezes. This red blood that everybody wants goes to the brain and back, the heart and back, the foot and back. They take oxygen out, it becomes blue, and then the cycle begins all again. And the reason I wanted to start with that is, if you were to look at a heart, right, let's just pick this one. There are big chambers here and there are little ones. All right, so that's kind of big. That one up there is tiny. Oh, look at that. That's just so darn big. The wall is just so thick. Which one is which? And that's easy, all right, because now we know that one of the chambers does the most work. The left ventricle is the one that's pumping blood to the brain and back, the heart and back, the arm and back, the foot and back, etc. So it makes up the apex of the heart. So when you see that point of the heart, that's the left ventricle, and it has the thickest wall. Once you know that, you're like, oh, okay, left ventricle. See, it makes up the apex of the heart, thickest wall, left ventricle. All right. Oh, there's a little chamber above it. See how thin that wall is? All right. So the little chamber above the left ventricle, that's the left atrium. All right. Now, on the other side, there is another ventricle. That's not the, go away. That's not the left ventricle, because the left ventricle is over here going to the apex. So that's the right ventricle. Over that is the right atrium. So if you're trying to talk about the chambers, first thing you do, find the left ventricle. Biggest wall makes up the apex of the heart. Once you know that, the left atrium is above that. The other ventricle, that's the right. It doesn't quite come to the apex. You notice where it ends, not quite at the apex, and it has a thinner wall. If that's the right ventricle, then that's the right atrium. All right, so there you go. All right, when I give a quiz on heart anatomy, there's what I refer to as the Big 12. My students have to identify the 4 chambers of the heart, the 4 valves, and the 4 vessels. And if you can get the left ventricle correct, the other one should fall into place. Those are the chambers. But now we have to talk about valves. Because so I'm going through a playlist that I have, and if you're interested in the heart or any of this, so my YouTube channel, Dr. Jan 41, has a whole lot more. Okay. So a few minutes ago, I said that there's a way that blood flows from the heart. It goes from the right atrium to the right ventricle to the lungs. It goes from the left atrium to the left ventricle to the aorta and throughout the body. That is the appropriate flow of blood. I'm going to use the word like appropriate because I don't want to use the word right, because then you might get it mixed up with right and left. So that's the way blood is supposed to go. But as we'll see in a few minutes, there are moments where it's tempted to go the wrong way, because blood's stupid. It's just going to go from an area of high pressure to low. All right, it doesn't know which way it's just going to go where it's pushed. And there are moments of the cardiac cycle where it is being pushed the wrong way. So you need to stop it from going the wrong way. So we have doors called valves. They open when blood is trying to go the correct way. They close when blood is trying to go the wrong way. All right, so we have 4 valves whose job it is to make sure that blood is only moving in the direction that we like. 2 of them we call AV valves or atrioventricular valves. Right, so they are between an atrium and a ventricle. So that's why they're called atrioventricular valves, because they are between the A, the atrium, and the V, the ventricle. All right. So you can always identify them because A, they have an atrium above them, but also they have these ropes coming from them. Now I'm about to say something. I like to only say things I'm sure of. I'll be honest, I am not positive of what I'm about to tell you, but I think I'm right. So if it's okay with you, I'm going to say it. All right. If you're a Harry Potter fan, right, you may remember that in the middle of the wands, it was like heartstring of a dragon, heartstring of a unicorn. That's what goes in the middle of the magic wands. You might have said like heartstrings. What's going on there? Well, I don't know, never having manufactured a wand. But what I think they're referring to are these. All right. So these rope-like structures, which are called chordae tendininae, all right, which are attached to the AV valves, but not the other valves. Semilunar valves don't have them, AV valves do. So there's 2 kinds of valve, and if you see these rope-like structures between them, that's an AV valve. On the little hearts that you have, if you look at the atria, right underneath each of the atria, left and right, you should see valves which have like structures on them. Those are the AV valves. So the right AV valve separates the right atrium and the right ventricle. The left AV valve separates the left atrium and the left ventricle. The right AV valve has three cusps, three flaps, all right? And so another name for it is the tricuspid. The left AV valve has two cusps and is called the bicuspid, and it's also known as the mitral. So if you have what's called mitral valve prolapse, and you're like, mitral valve, where is that? That's just another name for the bicuspid and the left AV valve. And if you're angry and you're saying, why are there multiple words for the same term? Left AV valve, bicuspid, mitral. Or if in other systems, if we said like uterine tube, fallopian tube, oviduct, same thing. Why are there multiple words? The answer is it's a big world. Lots of people practice medicine. And to get everybody to agree on using the same terms in common usage, well, it's amazing there aren't more cases where there's multiple common names for things. So those are the AV valves. The valves that separate a ventricle from the vessel that goes from it are called semilunar valves. They do not have those rope-like structures, and they do not have an atrium above them, right? The pulmonary semilunar valve is at the base of the pulmonary trunk. The aortic semilunar valve is at the base of the aorta. Right. Well, those are the 12 things, but let's review, all right? And if you want to follow along, you know, with the hearts, which I kind of passed out at the beginning, you are welcome to, right? Is that the wrong? Okay. So people at home, if you want to play with hearts, you can come next time in person and we'll give you hearts to play. All right. So on your heart, all right, the plastic ones, they're nice because they're painted. You know, two are painted blue, two are painted red, so that helps. Blue blood that nobody wants comes in the vena cava, which goes into the right atrium. All right. The right atrium will send blood past the right AV valve. I know it's an AV valve because it has these rope-like chordae tendinity attached to it, plus it has an atrium above it. That's an atrium, so it's an AV valve. It has these rope-like structures, that's an AV valve. So then all this blue blood goes to the right ventricle. The right ventricle squeezes. This will close, and we'll be talking about that in a second because we're about to switch over to the cardiac cycle. When this closes, the blood has no choice but to go this way through the pulmonary semilunar valve. It's not an AV valve because that's a vessel. That's the pulmonary trunk. That's not an atrium. And there's no ropey things there. All right, so that's not an AV valve. That's the pulmonary semilunar valve. So blood goes out that tube to go to the lungs. We then have red oxygenated blood come back to the heart through pulmonary veins. The pulmonary veins go into a left atrium. The left atrium sends blood past a left AV valve. Once again, there's an atrium above it. There's these ropey things, so we know it's an AV valve. When the red blood is in the left ventricle, that squeezes and sends blood past the aortic semilunar valve into this big red arch called the aorta. And the aorta is now going to start sending the red oxygenated blood. You know, some goes to the brain, some goes to the hand, etc. In my classes, this is a very quick version, and we skipped a little things like I didn't go into like the electrical stuff with cardiac muscle. I actually tell you what, I want to give you your money's worth. You deserve your money's worth. So when it comes to muscle, let's just quick. Everyone, think of a part of your body. Think. On the count of three, move it. 1, 2, 3, go. Okay. Back row, a lot of movement. Front row, not so much. All right. So people on the back. All right, back row. You were clearly thinking of parts of your body that have skeletal muscle. That's voluntary. So if you think of a part of your body and you try to move it, if it moves, you have skeletal muscle there. All right. People in the first row, I'm not quite sure what we're thinking about, but you were either thinking of your big toe or you were thinking of a part of your body that doesn't have skeletal muscle. All right. So there are other parts of our body which we can move. You can move your intestines and squeeze them. You can move your blood vessels and squeeze them, your lungs, et cetera, but not voluntarily, only through involuntary reflexes. So those are places where you either have smooth muscle, which is like everywhere, especially in the places we talk about 2 weeks from now. Or there's one more kind of muscle called cardiac muscle that is only found in one place called the heart. So you have 3 kinds of muscles in your body. Cardiac muscle is only found one place. And the big difference between it and skeletal muscle, a lot of it is what's called fast twitch because it'll do its thing in 1,000th of a second. When you get to cardiac muscle, all right, it now will like do its electrical thing and it holds it, holds it, holds it, holds it, holds it, and then goes. Skeletal muscle is 1,000th of a second. Cardiac muscle is 250 times longer. All right. So it acts a little bit differently, the muscle that you have in your heart compared to skeletal muscle. So I've got some more videos on that. It looks a little different under the microscope. So if you want to look at cardiac muscle, those thick bands you can see only cardiac muscle has those, right? But apart from that, we could say, you know what? All right, that's good on the anatomy. Let's move on to the cardiac cycle. Oh, I'm sorry, before I go, I'm sorry, there was one last thing I forgot. Do you know your blood vessels? Where is the red oxygenated blood? Is it in your arteries or your veins? Okay.
Arteries.
You are half right. Okay, so sooner or later, students realize I only ask you a question when it's a trick question, and they're like, "I'm not even going to answer." So your heart isn't doing 2 things. I'm sorry, it isn't doing one thing. It's doing 2 things. All right. So if we were to look at just an image, really quick. So here's an opossum heart. There's 2 things going on there. There's a right half of the heart that's pumping blue blood, and there's a left half of the heart that's pumping red blood. And if the heart is then doing 2 things, it turns out there's 2 what we call circuits, 2 loops of blood vessels. One of these loops is sending blood to the lungs and back. This is what's called the pulmonary circuit. In the pulmonary circuit, the arteries have the blue blood and the veins have the red blood. See, the arteries are going away from the heart to the lungs. You're not full of oxygen on your way to the lungs. You're full of oxygen on your way back from the lungs. So the arteries carrying blood to the lungs in this pulmonary loop, they are blue, and the veins that come back from the lungs, they're the red ones with the oxygen. But then there's another pump, all right? So while half of your heart is pumping blood to your lungs and back, the other half of your heart is pumping blood to your body systems and back, all right? And in this loop, now the arteries have the red blood going to the body systems, and the veins coming back have the blue blood. So the heart has 2 halves that are doing 2 different things. So we refer to what's called a pulmonary circuit, pumping blood to the lungs and back, and a systemic circuit, pumping blood to the body systems and back. Okay. Now, let's say they're not still young. I mean, just hypothetically, all right, when we wrap up this lecture, you could all go out dancing. All right, that's in the realm of possibility. Now, I'm looking at your faces. I'm not sure, that's top on your agenda. And I might be getting this wrong, but I think I know why. All right. Is anyone saying, I'm not sure if I want to go dancing, because you're afraid that if you do, you'll be out on the dance floor. And then all of a sudden, your arms start doing that and you hit the people next to you and you're embarrassed. Is that the reason? All right. So some yeses. Some of you are saying no, that's silly. I mean, my arms wouldn't do that unless I told them to. No, I don't have to worry about that. But then this is odd, all right? Because while these muscles don't do anything unless the brain tells them to, or spine, all right? Here, if we were to look at the heart and we were saying, okay, here's the heart. Oh, look at that. There's electrical activity there. See the star? It's on electricity. Did the brain tell it to do that? No. Did the spinal cord tell it to do that? No. The heart did. The heart starts its own heartbeat. All right. This muscle in my arms does what the brain tells it to. The heart decides when it wants to beat. Now, the brain and spinal cord may say, hey, it's an emergency. Maybe speed it up a little, like they can like influence its beat, but the heart establishes. You can take a heart out of a body, right? So hypothetically, like you're dissecting a frog, you take the frog's heart out of the body, it will still beat, even though it is no longer connected to the brain or spinal cord. Some of the muscles are what are called autorhythmic. That's what they do. They will then start this electrical activity on their own. Now, there's 5 such regions, all right? Now, just because I'm kind of in this mood, let's say we have a race. We say, hey, autorhythmic areas, race ya, all right? 1, 2, 3, go. And it turns out there's a winner. Out of all of the areas of the heart that can start their own electricity, this one wins the race, this one goes fastest. As a result, this becomes the primary pacemaker of the heart. All right, so a new heartbeat starts now because it said so, the SA node, the sinoatrial node. Now, all of these other areas could start, like the AV node can start a heartbeat, all right, but it would be a little slower than the SA node. All right, the AV bundle can start a heartbeat, the bundle branches can start a heartbeat, the Purkinje fibers can start a heartbeat, but it would all be a little slower. So if your SA node wasn't working properly, you might need an artificial pacemaker to stimulate the heart and to tell it to start a new beat. Because while these other areas could take over, they would be slower. The AV node would struggle, like maybe you would go from 75 beats per minute to 60. All right, but once you get to the AV bundle, now you're down to like 45, and so it just, you would need an artificial pacemaker to keep that going. We'll get back to all of these because this will all come together with like ECGs and things like that. But if someone said, like in a heart attack, what happens? Well, it depends. Like if you were to say like they just blocked a road in Middletown, what's that going to do to traffic flow in Middletown? I don't know. I mean, well, back it up. But are we talking about South Street? Or are we talking about 84? All right, because that's different. All right, so blocking a street depends on what street it is, where like the effects will be different. So if I have a heart attack and heart muscle dies, all right, what's the effect? Well, I don't know. Was it here? I hate to have those cells lose or die, but to be honest, I might not notice. All right, the left atrium, it doesn't have to work all that hard anyway. Like, so I could lose some cells here and not, notice. But if I lost the SA node, that's huge. So not all of the heart is doing the same thing. So the effects of one heart attack could then differ from another heart attack. And any of the ones which influence these yellow areas would be especially bad. And we can get back to that. So the cool thing about electricity is at no point do I have to say, trust me. You just need to trust me on this. All right. And science, we don't like that. Like, don't trust your teachers. Like, just say, show me. And electricity is not this mystical, invisible force. You can see it. You just put you put electrodes on your head, you can see an EEG and you can see the electrical brain activity. You put it on your muscles, you can see their activity. If you put it on your chest, your arms, your legs, you can now see electrical activity. And for a while, you see nothing, 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 nothing. And all of a sudden you say, ooh, look at that, a little blip. All right. And then you go back to your baseline, you go nothing, 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 nothing. And then all of a sudden, all right, it goes this weird thing. It goes down, it goes up, it goes down. So this weird thing, all right. And then it'll go back to nothing, nothing, your baseline, nothing, 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 nothing. And then it'll do one more blip, and then this pattern will repeat itself again. All right. So we can measure the electricity of the heart. And we realize, and once again, just because I'd like to fit in, like the whole picture as opposed to like, all right, wait till next class and we'll go through this. I'm squeezing this in a little bit. Remember how I said the heart muscle, like it'll do a change, start electric and then hold it, and then, finish? That's what we're looking at. Because the atria go first. All right, so once the SA node says a new heartbeat has begun, the atria get the message right away. But the ventricles, they get it second. So what we see is the atrial muscle says, ooh, a new heartbeat. electrical change, start contracting. And we see, ooh, see this blip? That's an electrical change. They now have the message to start contracting. But remember, they hold it, hold it, hold it. During that time, there's no new electrical change. All right, so that's the hold it. And then we get to here, and the atria say, okay, we're done, go back to normal, and that's an electrical change. So the first half of the cardiac cycle is the atria stuff. And then on an ECG, this is where they start, and this is when they finish. But at the same time that they're finished, when the atria are repolarizing, that's ending as opposed to depolarizing, which is beginning. That's when the ventricles finally get the message, and now they depolarize. So the atria are finishing at the same time the ventricles are starting. All right. So then they say, oh, new heartbeat has begun, electrical change. You see the electrical change. Then they hold it, hold it, hold it until they say, oh, we're done now. Let's go back to normal. All right. So the heart does not contract as a unit. It contracts as two units, atria, ventricles, atria, ventricles, atria, ventricles. So when you look at an ECG, atria half, ventricle half. And all right, so we'll talk about abnormal ECGs in a little bit and what they might mean. But this is, like if someone had an ECG done, it's like, ooh, there's something here going on with the P wave, or there's something going on with, the point between P and Q, the PQ interval. Or you see this, it goes down for Q, it goes up for R, it goes down for S. That's the QRS complex. I'm seeing something on the QSR complex. I'm seeing something here on this ST segment, if that's S and that's T, or I'm seeing something in the T wave. I'll give you examples when we're done. But like if someone says there's an abnormal ECG and they start throwing out those terms, this is what they're referring to. So one, so I apologize. I do want you to learn stuff, all right? But like I've taught a long time. That doesn't always work. So fallback is even if you don't learn something, I'd like you to leave here sounding like you learned something. All right. Like I'd like you to have these big words that you could throw out in conversation. Everyone else at the table says, so smart. See how big that word is. So two big words for right now. One is systole, that means contraction. One is diastole, that means relaxation. So the other people at your table, all right, they're just going to say contracting or relaxation, but you're going to say, oh, the heart's in systole or diastole, and they're going to say, ooh, so smart. So if you were to say, when are the atria squeezing blood? All right, well, that would be in the first half of the cardiac cycle. So atrial systole goes from partway through the P wave to partway through the QRS. So the atria are squeezing in the first part. The ventricles are squeezing in the second part. So ventricular systole comes second. Okay. Now, this is hard. All right. It's seriously in my AMP2 class, I think the cardiac cycle is the most difficult thing. I'd like to expose you to it because it's important, but overview, it's here if you need more. And I've got all this stuff like I have songs. I have these characters that this is diastole and that's systole, left ventricle woman, and there's right ventricle man. And so there's those things. At some point, there's wrestlers and they start pushing each other. And you can say at this part in the heart cycle, left ventricle woman is big and she can push the right ventricle man. So I'm just going to go through this, quickly. But if anyone says, ooh, I'd like to, get a more profound understanding of that, you'd be welcomed. All right. So let me just kind of go through this incredibly complex thing. But if maybe 3 times, like really fast. All right. But let me just do the electricity first. All right. And then maybe the next time, then we'll talk about the valves. All right. So it's not like too much all at one time. Let me just kind of, just build layers. So a new heart cycle. What's going on? Well, the first electrical event is the SA node says a new heartbeat begins now because I say so. All right. So first part of a new cardiac cycle. And the message will go to the atria. All right. When the message gets to the atria, they start this electricity thing and it looks just like sparkles. So I swear to you, it looks just like that. All right. Exactly. All right, so the sparkles on the cardiac muscle, that's what it looks like. And we can see that that's the P wave. So when the atria start to sparkle with their change, that's what we see on the ECG. That's a P wave. But then they're just holding their systole. They're not, doing anything new for a while, all right, until then they repolarize at the QRS. And that's, they repolarize, and that's when we'll, there'll be more sparkles coming up. Yeah, there's the sparkles, and we get the QRS. So the atria are now done. All right, they're electrical events of the first half. But by now, that message has spread from here, the second of the 5 autorhythmic areas, to here. So it goes from the AV node to the AV bundle. All right, I swear, to the right and left bundle branches, to the Purkinje fibers. And once we get through there, that's when the ventricles get their message. And now they can do their sparkle thing. So they'll sparkle in what's called the QRS. That's when they begin. All right. And then they'll squeeze and not do anything new electrically. So that's where we get a straight line here. And then they'll sparkle again when they're done. They repolarize. And that's the electrical events in the cardiac cycle. Any questions? I don't care because I'm going to do it again. All right. But this time, all right, we're going to add in what the blood is doing at the time. So I apologize. People at home, I'm going to run to the door a couple of times. All right, you know what? Maybe we'll do it. All right, we'll live bravely. Let me just see. I can see this. I have unplugged computers, and then so by trying to switch this back and forth, I've done this wrong. I've made some problems, but like, I think it'll work. So people at home, I'm going to run over here for a little bit. Okay. Let's talk about the blood. Let's imagine that we're in a heart, and that this is a ventricle, and that this is the atrium. Okay, so the atrium is out. While the ventricles were squeezing in the last half of the cardiac cycle of the previous heart, blood was coming in. So if this is the right atrium, blood was coming in from like the vena cava. If it's the left atrium, blood's coming in from the pulmonary veins. Right. The left ventricle just squeezed out all of its blood, so it's empty. This is empty, no pressure. Now a lot of blood here. Right? When a new cardiac cycle starts, all the valves are closed. So we start with all the valves closed. But that's about to change because there's pressure here. Right? The atria is full of blood. The ventricle's empty. So there's pressure. So the high pressure on the AV valve is going to force it open. So the first thing that we're going to see in the cardiac cycle is that the atria, being full of blood, all right, they then push on this AV valve. So the valves are going to open and close because of pressure. We don't pull them open. We don't pull them closed. It's just pressure. All right. So because the high pressures in the atria, the lower pressures in the ventricles, this pushes the heart valves open, and now the blood starts to go from the atria into the ventricles. Actually, most of the filling is even done before the atria squeeze. The squeezing helps get out the very last bit, but it's mostly just gravity that takes care of it. Okay, so the atria squeeze in the first half, right? But the atria stops squeezing, and now the ventricles start. So if you're a ventricle, that means the walls are starting to close in. And the blood that's in this chamber just wants to go from an area of high pressure to low. There's a big empty hallway out there. So if you're being squeezed in here, you're like, oh, that's awesome. Let's just go. I'm sorry. People at home. I think I'm pointing the right way. Nope. There we go. We just go here, all right? So if I were to say, oh, and you probably won't like this, but my students will. If I were to say, you know what? I'm tired. How long day? I don't feel like teaching anymore. So just go home. Let's just call it a day. Go home early. See, you're not happy. My students like, oh, it changes how they view me. Like, oh, I love my instructor now. So if you just get your book bags, etc., and you're like, oh, okay, I'll go. Little do you know, I've got like a friend out here with some fishing line, and just when you come up here, like, yay, I get to leave class early. All right, someone pulls this shut, and now this shuts. Why? Because this valve opened because of pressure. When the pressure's going this way, it will open when blood wants to go the right way. But when blood wants to go the wrong way, that's why these cusps are here. The blood, as it tries to go here, just touches the cusp and pushes it close. So if this is the bicuspid, there's one cusp that closes here, and there's one cusp that closes here. And those ropes are now taut. The reason the door doesn't go into the hallway and flap around is because the rope gets pulled taut here. So it's pressure. When blood tries to go the wrong way, okay, pressure then pushes it closed. And if we have students out here, I always like start to involve them in the class, which they hate because they're like, what are you doing? Why are you involving them? So I would say if there were students here, they can tell the difference between you sitting calmly or you coming, oh, let's go, my instructor let me leave early, only to have the door closed, and now you all jostle into each other, bang book bags, and go home, and you say, I hate my instructor, he's the worst, etc. That makes noise. So in a cardiac cycle, there are two sounds, blubbed up, blubbed up, blubbed up. The first hard sound is right here when the AV valves shut and the blood starts swirling around. Just like if all of you start going over here saying, hey, and the door shuts and you're like, oh, I hate my instructor, and you go home. That swirling, that turbulence would make noise. People in the hallway would hear that. And if your blood starts swirling around, all right, if you have a stethoscope over the chest wall, you hear that. All right, so that's the first heart sound, the lub, when they're swirling in the blood after the AV valves shut. Okay. We'll get to the second heart sound in a second. So the ventricles start to squeeze and the AV valves shut. So is everyone all right? Is anyone scared? Okay. Because the walls are closing in, I said that, and there's no way out of this room, right? The windows are closed, the door's closed. So there's this split second where it's kind of scary. We're just squeezing this blood and there is no way out. And as a result, this blood pressure just goes up and up and up and up. But at a certain point, it now gets higher than the window. Now, people at home, I apologize. I don't think I can swing this without breaking stuff over here. So I'll be right back. All right. So if we were to go over here to a window, as we squeeze harder and harder, it turns out there's already blood out here. Like if you get your blood pressure, it never goes down to zero. Like maybe it's 120/80, never goes down to zero. So there's pressure out. Someone is pushing on this window. But as the ventricle squeezes and squeezes and squeezes, at some point we are pushing harder here than they are pushing on the other side. So now we can push this semilunar valve open. That's the AV valve. This is the semilunar. So as we push this semilunar valve open, now the ventricles can eject blood. All right, so we squeeze and squeeze and squeeze, and at some point, this pressure is higher than the pressure in the aorta and the pulmonary trunk. The semilunar valves open, and we eject blood. So the right ventricle is sending blood to the lungs and back. The left ventricle is sending blood to the body systems and back. But nothing does systole forever. I mean, the squeezing doesn't happen forever. So when the ventricles stop squeezing, they're empty now. They squeezed out their blood. They're no longer squeezing. All of a sudden, we go back to the window. There's a lot of pressure outside the window, just squirting a whole lot of blood that way. And this chamber's empty. So where's the high pressure?
I can't read that, but you can take it.
This is low pressure. And so the blood wants to come back. We don't want it to come back. We want to go
Thunderstorm. Those will be isolated in nature. So I think most areas will avoid the rain tomorrow. And if you happen to have some rain develop, it's only going to last for a little while. So much of the day is going to be quiet. So
okay. So give me a time. I'm sorry. I'm just going to.
On the lake. Just keep an eye on the weather and the.
Always a good idea to keep an eye on the weather. Okay. I think we're good. Yeah. Okay. So that was the second heart sound. So if you put stethoscopes over the chest wall, you hear lubbed up, lubbed up. The lub is the turbulence in the blood when the AV valve shut halfway through the cycle. The second heart sound, the dup, is when the semilunar valves shut and there's turbulence in the blood at the end of the cardiac cycle. Okay. Now, that all works great, but sometimes there are problems. It's like, what would happen if a valve doesn't close all the way? Like, if there was still a crack in the door, all right, then some blood would squirt out. And instead of hearing lubbed up, you would hear lub, okay. That would be what's known as a heart murmur. And there's a couple of reasons for that. It could be a valve that doesn't close completely. It could be a calcified valve flap that's not as flexible anymore. It could be a valve in a slightly wrong position, like mitral valve prolapse. Is the mitral valve is just a little too high, it's prolapse. So that's a problem with the valve. I'm going to talk about ECGs in a second. ECGs are the electrical stuff. Valves, the heart sounds are the valve stuff. All right, so if you have an abnormal heart sound, that's not necessarily electrical. That's like your flap doesn't close completely, or it's calcified, it's not flexible. The ECG is the electrical stuff. So they're not interchangeable, the lub dups and the ECG stuff. Okay. So there's a song, there's a few other things, but why don't we jump down to the ECGs, and then we can maybe talk about heart disease a little bit. And once again, like, you know, we're winding towards the end, but, you know, we could have, you know, pushing contests between the valves, you know, where one's stronger than the other, you know, et cetera. But you're here somewhere, I swear. There we go. Okay. So one of the songs as you came in was the abnormal ECG song. Let me just to go through this. And I'd like to just talk about a gentleman who I shared an office with for decades. Dr. Kahneman had some gallbladder issues, and to go to the hospital, he was going to have his gallbladder removed, and he had some tests done. And they said, wait a minute, I don't like these tests. Let's do those again. All right. And they said, okay, you're not having your gallbladder removed. You're going to the surgery now. We're putting in, you know, some stents. Right. So heart disease is really hard to talk about because the first symptom that about 1/3 of people show is that they have a heart attack and die. From a medical standpoint, it is difficult to treat a disease when the first symptom is death. So any advanced warning you can get of this, obviously that saves lives. All right. So ECGs are the most non-invasive things in the world. Someone puts a little sticky on this list, a little sticky on this wrist, with some stickies on your ankles, and you're good to go. Now you might say, wait, you know, they had to shave my chest and put a bunch here. Well, so yeah, they could do that. I mean, you can get a general one with just your wrists and ankles. But if I were to take a picture of this room, okay, it would look different depending on whether I was standing here. The picture would look a little different than if I was lying down, looking up, or standing. So different positions give you a different picture, and you might see something on one picture that you didn't see on another. Plus, the heart might look just fine when you're sitting down, all right? But if you're stressed walking up a flight of steps, now all of a sudden an abnormality, you know, is evident. So what you'd like to do is to stress the heart, like have it, you know, maybe on a treadmill or a table that's tilting or something, so that you could see that, because you don't want to say, oh, you're fine, go home, and they go to shovel snow and they have a heart attack, right? You don't want that. So if you want someone to move, well, now all of a sudden this is a problem. You've got these little stickies on your arms and your feet because you're moving them, and now you got muscle electrical like here. So then like heart has some leads which are over the chest. They would help. Some people even swallow an esophageal lead. So, you know, we're taking pictures of the electrical activity of the heart, and you might want to take, you know, a picture from this angle being better from this angle. And if you're going to be doing a stress test, then the ones on your chest might be more valuable than those. Yeah.
What tell us about a nuclear stress test as far as the complications?
I don't know of any, but I'm not an expert on nuclear stress tests. Sorry. So I'd like to just go through some examples. All right. So if a normal ECG looks like this, and all of a sudden you look like that, and you're like, ooh, that P wave's bigger than what I thought it would be. And then your next question is why? Now, maybe you're super athletic. One of my students once was like ran track for West Point, and like their things were huge, a huge P wave. And we're like, oh, I know the reason your P wave is so big, because you're the super athlete. But for someone else, it might be your AV valves are narrow, and now your atria are getting more muscle to compensate. So that was something that you didn't know. Once again, you could get this in 90 seconds. You just need stickies on 4 limbs, and all of a sudden you're getting data. So this is non-invasive, and you're just learning about the heart. Sometimes the PQ interval is longer than it should be. You see that? Just longer. Now, you say, why might that be? One of the things would be, all right, well, my essay note says a new heartbeat starts now. But if you've already had some heart attacks, you've got scar tissue that might slow the message from getting to the next section. So once again, this is non-invasive. And in 90 seconds, we just said, I think you've had a heart attack before. I mean, that's incredible information to get, especially since we don't want the first symptom to be death. All right. So there's lengthened PQ intervals. I've got a couple different variations on lengthened PQ intervals. Let me just kind of jump ahead to here. All right. So lengthened PQ intervals and scar tissue can give you a couple of things. I give you some of those. All right. So let's say someone does an ECG and you're saying, okay, P wave looks fine. PQ interval looks fine. Like, ooh, look at that R. That R looks bigger than what I was expecting. That could mean a couple of things, but it could mean you're having a heart attack, which is good to know, all right, for a couple of reasons. Like, let's say it's Thanksgiving dinner, all right, and two people at your table say, I'm not feeling so good, and someone says, I think I'm having a heart attack, you should call 911. Well, maybe they're not. Maybe they just swallowed food and it's stuck over their stomach and their esophageal sphincter won't open. Their heart is fine. They just know their chest hurts, but it's not a heart attack. They just don't know that. The second person who says, no, I'm just feeling a little bit off, don't call it 911 for me. Turns out they are having a heart attack. So the point is, sometimes you think you're having a heart attack when you're not. Sometimes you don't think you're having a heart attack when you are. You could have these when you're asleep. It's nice that they leave signs. If you're on a monitor overnight, someone can look at it and say, like, I know what happened to you. All right, you were having a heart attack. If you have this next one, you were having a bad heart attack. All right, so your ST segment could not, instead of being flat and being at baseline, it could now be elevated. All right, so you see how high that is? It didn't go down there. That's not just a heart attack, that's probably a bad one. All right, so good information to know. If you're having a serious heart attack, I mean, everyone, needs to know that. That could save your life. And my favorite is if you notice the T wave, and it's just a little lower than it usually is. I mean, heck, sometimes it's even upside down. Like, see that? That's just not as high as that. That means you've probably got blood vessels blocked, all right, going to your heart. All right. Are you having a heart attack? No. But tomorrow you could, or next week you could. Like, you're getting close. Right? That's beautiful. And that saves lives. All right, so now someone isn't going to go about their business. They're going to say, all right, we need to schedule the stent. We need to schedule the bypass. We need to do something, all right, because your blood vessels are blocked to the point where your ventricles are not getting enough oxygen. So here's, if you ever had, an ECG done, there might be like talk about this T wave, this ST segment, et cetera. It's just a quick introduction into why that might be important. In our last couple minutes, I just want to maybe just add one more. I can't seem to get past. Go away. Okay. Hey. I just want to say a few things about heart disease. Now, the 5-minute version could easily become the hour version, but I think I can just make this clear in the 5-minute version. Heart disease is the number one. Okay, so as this smart person was just saying, heart disease is the number one cause of death in the United States and the world. And it's linked to stroke, which is number 3. All right, so what I'm about to go through, this is something that affects most of us at some point, whether directly or through people that we know, et cetera. So what happens is, I'm still in that. Okay. So what happens is, your blood vessels should look like this with these 3 layers, muscle in here, blood going in a hole in the middle. All right, so the middle, that's where the blood goes. All right, so that's how we all start off. But at this point in our lives, all of us have at least a little of this, all right, where lipid plaques are starting to develop in your blood vessel walls, which are now making this narrow. It's not a question of if that's happening, it is. All right. The question is, to what degree? Because if you start to occlude it a lot, that's a problem. Like now, blood has nowhere to go, so now your pressure is going to be super high. But also, if you've got a clot that forms somewhere, All right, this is so narrow that the clot might get stuck there. And now the clot's going to block blood flow. Anyone who's downstream from this isn't going to get blood if this is happening in the heart. We call it a heart attack or a myocardial infarction, and heart muscle dies. If it is happening in the brain, we call it a stroke. Now, I hate to play favorites with my body, but if I lose some skin cells and cutting myself, I don't care, because they divide. I replace them. I'll be good as new in no time. My heart muscle cells never, ever divide. I have as many heart muscle cells now as I will on the day of my death. If I lose some today, I just have to live the rest of my life with fewer. I don't get them back. The same is true with most of the brain. Not all of it, but almost all. All right. So I don't want this to block blood flow so that heart muscle dies or brain cells die, because then I'll have to do without. So then the question, and once again, I'll just very quickly, what causes this? Well, there's a term that we use which is called multifactorial. All right. So that means a lot of things can cause this. And like some are genetic, some are environmental. And I go through them in great detail here. I'm just going to hit a few highlights here. So let's say cholesterol. All right. So there's a normal way that cholesterol travels. And there are genes that make proteins, and I give them different colors there. Well, it turns out some people have a weird dark blue protein. You we have different hair colors, we have different heights, we have different ears. Some of us have different blue proteins. Some of us have different aqua proteins. So now genetically, because your aqua protein is a weird shape and doesn't bind this as much, genetically you are predisposed to heart disease. That doesn't necessarily mean you'll get it, because this aqua protein is functioning in lipid transport. So if you have really good lipid levels in your diet, maybe having a bad gene can be compensated by a good environment. If you eat like a whole lot of lipid, you say, like, oh, this person eats horrible and then they get heart disease. Well, they have a bad diet, but maybe they have good genes. So that's why this is complicated. There's genes and environment. Oh, but there's more, because not only can we send blood to our body cells, including the plaques, where the plaques might get bigger. That's what we call bad cholesterol, the cholesterol that's going that way to potentially the plaques to make them bigger. We can also send cholesterol the other way. The liver puts it into bile and we excrete it from our bodies. We call that good cholesterol. Actually, cholesterol is just cholesterol, but it can be in two different packages. All right. Now, notice there's different proteins here. Like there's a red one here, this purple one. So here are two more genes that some people have weird versions of. So, for example, let's talk about the red one. I have one form of the red gene called apolipoprotein E4. That means I have a slightly higher risk of heart disease and Alzheimer's than if I didn't. And just given the number of people in the room, I know I'm not the only person who has one E4. If both of your parents gave you an E4 allele of the red protein, you're at a really high risk of heart disease and Alzheimer's. So there's an aqua protein, there was a dark blue protein, there was a purple protein, there was a red protein. And these are just the ones involved in cholesterol. There's so many other genes. This is going to go super quick. We're like, we eat cholesterol. You make cholesterol. Sometimes you eat less. Now your body makes more. Your blood cholesterol actually goes up, even when you cut it from your diet. You cut fatty acids out of your diet. Your body knows how to make fatty acids. Your fatty acid levels go up. But you see all these proteins, we vary. Just like we vary in height and hair color, we vary in these. Some of us make more cholesterol than others. All right. It's not just cholesterol, it's oxidized cholesterol. So if you oxidize cholesterol, now that's really going to affect your risk of heart disease. What does that? Well, air pollution does, smoking does, not having enough antioxidants either in your body or your diet does. There's a whole bunch of things. So here's some genes that could mean you oxidize your cholesterol more, which will make it worse than regular old cholesterol. But environment like air pollution can have a role in that as well. In the rest of these videos, I start talking about how white blood cells called monocytes eat all of the cholesterol, thinking that they're doing us a favor, but then they just become these big toxic bags of fat called foam cells that will actually make it worse. So why are they doing that? All right, well, there's both genes and environmental factors which could influence this. For some people, cholesterol and lipids aggravate your heart disease risk. For some people, not as common, it's protein. You have homocystinuria. It's the protein in your diet that's aggravating this. So that's genes and environment. That's a whole nother set. Your blood pressure is relevant. So now we start talking about all of the things which can make blood pressure go up or down, both genetic and environment. There's fat, but there's different kinds of fat. All right, so like fat from fish can lower your heart disease risk. Fat from beef or chicken can raise your heart disease risk. So if you wanted to estimate a patient's risk of heart disease, and remember, if a third of people who have heart disease, their first symptom is that they have a heart attack and maybe die, you want to predict risk. Like, we're worried about you. You're going to take these preventative measures. You're fine. You can go about your business. It turns out it's complicated. There's all of these genes which can contribute to risk. There's all of these environmental factors. It's not just what's your cholesterol. That's a factor, but that's just one of many. All right. So this is involved in heart disease is an example of what we call a multifactorial trait. So this was just meant to give an introduction to heart, how it works, talk a little bit about ECGs and heart disease. Once again, if this is the #1 cause of death and stroke is #3, this touches so many of us, whether directly or in people that we know. So understanding a little bit more about it, hopefully this was helpful. Does anyone have any questions? Yes.
What's #2?
Good. I should know that. I think it might be asthma and respiratory stuff. Okay. But I think, but I'll have to go back. Yeah.
Heart is its own.
Yeah.
All right. So is a chemical reaction to do that?
So it sounds super fancy that the cells do electricity on their own. I hate to spoil it. It's not really all that fancy. I'll explain it, but I'm going to burst the bubble. So I'm sorry. So a battery, what makes a battery? What gives you voltage is you separate charge. All right, so you've got a positive area and a negative area. And when the positives go to the negatives, now you have a flow of electric current. That's what gives you electricity. So the separation of charge is what gave you voltage. If I'm a cell membrane, what do? I pump ions. I pump the sodiums this way, I pump the potassiums this way, and now the outside of the cell is positive, the inside of the cell is negative. So there's voltage across the cell membrane. All right. So just like your battery has voltage because you separate a charge, cell membrane has voltage. And in these cells that you're talking about, they leak. They've got these little doors which are partway open. So we separate the sodium, but then it all starts leaking in. So the electrical difference across the cell membrane just gets all of a sudden now it triggers what's called an action potential on its own just because the cells leak. So yeah, I think it's fun. It's fancier the first way. It's just like, ow, that's not as fancy as I thought. Yeah. Oracle.
One spot, now they want to put the plugs in there.
Watchman.
Yeah, the watchman, and there should be a cooling in that.
So
If you go into AFib, it control possibly.
So they say that the atrial appendage is what they call it, like a little area that.
So we do have, I'm familiar with this term. And you could even see it here, like we have these little flaps, which are called auricles that just give just a little extra space. Like, so the atrium just has to be a chamber. We have this little extra to flap here called an auricle. I imagine, like, if we were to look at everyone's, large intestines, we have these little bulges out of them called epiploic appendages. So, like, there might be, your small intestine, and you can have diverticulitis, et cetera. So, like, this is an extra little flap that I know of. I wouldn't be surprised if, like, there's another. It just gives the atria a little extra room to hold blood. Anybody else? Was someone at home saying something? Yeah.
We have AFib and atrial coronary ablation. It's just a standard area of the heart.
Okay, so there were those 5 areas that are autorhythmic. Now, if I was a heart muscle cell, I would say I want to be one of the autorhythmic ones. That sounds really cool. So sometimes one of the other areas that isn't yellow says, I want to do that too, and they become yellow. Now, maybe genetically you're a little more predisposed to this, but something like a lot of caffeine could push normal heart muscle cells into your autorhythmic too. So someone could go to the hospital and like their heart rate's 180. And you're like, why is your heart rate 180? Is your SA node doing that? No, it's this other area. This other area says, I want to help too. I want to say, hey, heartbeat, heartbeat. So it's what's called an ectopic focus of a heartbeat. And what you have to do is you kill it, or you have to say like, you're going to die, and you just have to destroy those cells. So that could be what you're referring to. Let me just define the term fibrillation for a second. Remember how I said the heart contracts as 2 units, atria contract, then ventricles contract. Imagine we're doing a tug of war with the class next door, like you can take them, you're better, I have the feeling. But what we need to do is all of you need to pull at the same time. Look, we will do heave, and that's how we win. If you give a little tug and the next person gives a little tug and it's all unsynchronized, we're gonna lose, all right, because we're not generating a lot of pressure at one time. So if your heart chambers are twitching, or a little tug, a little squeeze, that's what's called fibrillation. And just like if you were all talking, like my students, and I would try to get everyone back on task, I could yell like, stop, and hope you would all do this, and now get on task again. If you put a strong electric current through the heart, if they're twitching, each one on its own cycle, you could say, stop, silence them all, and then hopefully the SA node starts, and now everyone decides to follow, and you can return to a normal heart rhythm. So that's what a defib machine does. The fibrillations are all twitching out of synchronous, and a defib passes a strong electric current to try to get them back. Thank you so very much for coming. Next week, we do the brain, the most complex structure in the known universe. And 2 weeks, we do as many systems as we can fit in to answer any questions that you have, like respiratory and urine. How are you doing at home? Any questions? There was something in the chat. Oh, thank you. Thank you, Rhoda. Good night, everybody. If anyone has a heart, I'm sure you all have a heart. Great.